Welcome. In this video I'm going to show you how you can perform a Neyman Goodness-of-Fit test using Microsoft Excel. I have a separate video where I use my own add-in where I simply have a function to do this, but in this video I will not use that. I'll simply use plain Excel. In the video we'll focus on how to obtain the output, not so much if you should be using this test, because there are quite a lot of alternatives for this test. Probably the most common one is the Pearson Goodness-of-Fit test, and the main difference with this test is it actually swaps the observed and expected counts. So to get started we need some example data to show you how it can be done. So in column A I have some data. It's taken from the General Social Survey from 2012. I changed a few things along the way in the years, so I always call this the adjusted version, but it's just some things might be slightly different if you download the original file. We need to know the number of categories, in this case 5. You can simply copy paste the entire column and then do a remove duplicate. So under here you can then say if you copy paste it, you can actually go for data and then, here it is, remove duplicates. But in this case I already know there are 5. It's actually these 5. And the first thing we need are the observed counts. So simply do a count if, then the entire column, and the criteria in this case is then married, so I can copy paste it down. It will keep column A and will just adjust those the categories. Now I'm using a semicolon because that's how my Excel is set up. In your case it might actually be a comma to separate the parameters. The expected count, either you can just enter them if you know them or what you actually would expect. Otherwise it's quite often simply the entire sample size divided by the number of categories. So you then simply take the sample size, which is the sum of all of these, and then divide it by the sum of all the frequencies divided by the number of categories. So this one is indeed simply the sum of those. Alright, after that what we need to calculate is this, the observed counts minus the expected counts squared divided by the observed count. So notice, for those who are familiar with the Pearson chi-square test, this simply flips it. And the Pearson would be the other way around. It's still observed minus expected, but then divided by expected. Alright, so that's what's being done here. We simply take the observed minus the expected, square the results, and then divide it by the observed. I can copy paste it simply down, and as you can see it will adjust accordingly. Then the chi-square value is simply the sum of these, so we'll sum all of those up. We also need the degrees of freedom, which is the number of categories minus 1, so that's the number of categories, and then minus 1. And then to determine the p-value, also known as the significance, there are a few different formats to do this. You can simply use the old chi-dist and then simply say, well, it's the chi-square value and the degrees of freedom. You can do 1 minus the new chi-square dist and then set the cumulative to true. You can also immediately do the new chi-square dist right tail. And you can even perform just a chi-square test where you then enter the observed and the expected counts. However, in this case what you then need to do is you actually need to reverse the two. So the actual range should be these, and these should be these. So that should actually then, so it should have been like this. I should have adjusted and that should give you the same result. Now this p-value, if it's below a certain threshold, usually 0.05, you would reject the null hypothesis, the assumption about the population, which usually is that are these expected counts actually, so that it's distributed equally. So in this case we would reject that assumption and would say there is a significant difference among the categories. To find out which one exactly, you'll then need to do a post hoc analysis. There are also some so-called continuity corrections. Yates, for example, that should actually only be used if it's a 2x2 table. It mentions to add or subtract a half depending on if the observed counts are greater than or less than the expected counts. I also include that if it's the same, not to change it, but those criteria somewhat change depending on which author you're following. So what I've done here is simply copied the observed and the expected counts, and the adjusted one just done with a simple if function. It looks more complicated than it is. This states if the observed count is greater than the expected count, then subtract a half. Otherwise, if it's less than, then add a half, and in all other cases simply use the original one. I can then copy paste this formula down. And then you have to do all the calculations again, but then using these adjusted frequencies. Alternative, what you can do is the Pearson correction. The Pearson correction says to take the sample size minus 1 divided by the sample size, and then you multiply the original chi-square value with this correction. The Williams correction is another one. It says to take 1 plus the number of categories plus 1. So it also takes the number of categories into consideration. Divide that by 6 times the sample size. So that's your correction factor, but be careful in this case. We then divide the original value by that, and then we get a new chi-square value of 1814. Alright, and that's it. I hope this video was helpful, and thank you for watching.